In today's video, we're going to be going over thermochemistry. So let's start with kinetic energy. Kinetic energy is the energy that an object has because it's moving. The faster it moves, the more kinetic energy it has. For example, a moving car or a rolling ball, they both have kinetic energy. So let's move on to potential energy now. Potential energy is the energy stored in an object because of its position or condition. An example could be a roller coaster right before it's about to drop, or it could be a book on a shelf. Now let's move on to the law of conservation of energy. So this law states that energy cannot be created nor destroyed, but it can only be changed into another form. For example, if you drop a ball, its potential energy at the top turns into kinetic, but the whole energy stays the same. Now let's talk about exothermic and endothermic reactions. Exothermic reactions release energy usually in the form of heat to their surroundings, and whereas endothermic, they absorb energy, again usually in the form of heat. Two examples of exothermic reactions can be burning wood in a fireplace, which releases heat, or a firework explosion, which also releases heat. For endothermic, two examples can be of photosynthesis, in which plants absorb sunlight, or melting ice, in which it absorbs heat from the surroundings. Now let's talk about graphs. An endothermic reaction graph shows the energy needed to start the reaction and the energy absorbed through the process. You'll see the energy levels increase as the reaction goes on. So an exothermic reaction graph shows that energy is released during the reaction. The energy of the products is lower than the energy of the reactants. The difference is the energy that is released. In an endothermic reaction, heat flows into the system. For example, when you heat up a chemical in a test tube, the surroundings get cooler because the heat is getting absorbed. In an exothermic reaction, heat flows out of the system, so the surroundings get warmer. For example, when you light up the candle, the flames gives off heat into the air around it. A heating/cooling curve shows how the temperature of a substance changes as heat is added or removed. The curve shows the temperature staying constant during the phase changes because the energy is used to change the state, not increase the temperature. Phase change happens when a substance changes from one state of matter to another. It could be from solid to liquid or liquid to gas. This happens when energy is added or removed. So the relationship between temperature and energy during a phase change is that the temperature doesn't change, but the energy is still being absorbed or released. This energy goes on into forming bonds between molecules. Whereas when there's no phase change, energy added to a substance increases its temperature. As the temperature rises, the molecules move faster, just like when you heat water. A phase change diagram shows how a substance moves between solid, liquid, and gas as heat is added or removed. It usually shows flat sections where the substance is changing phases. So the relationship between changes in temperature and pressure during phase change is that when pressure increases, the boiling point of a substance goes up. So under high pressure, the water will boil at a higher temperature. When the pressure decreases, the boiling point goes down. The critical point is when you cannot distinguish between the substance's liquid and gas phases anymore. After this point, there is no difference between them, no matter the pressure or the temperature. So there's a formula for calculating heat energy. It's called Q equals mc delta T, where Q is the heat energy in joules, m is the mass of the substance, usually in kilograms, C is the specific heat capacity, and delta T is the change in temperature. Specific heat is the amount of energy required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. And of course, different materials have different specific heats. Two examples can be water, which has a high specific heat, meaning it takes a lot of energy to heat it up. And it can also be metals like iron, which have a low specific heat, so they heat up and cool down very quickly. So over here, I did a heat calculation. Let's go. So let's see, you want to calculate how much energy it takes to heat up 2 kilograms of water from 20 degrees Celsius to 40 degrees Celsius. The specific heat would be 4.18 joules per grams degree Celsius. So now you got to use the formula, which is Q equals mc delta T. So what you're going to do is you're going to take 2,000 grams, times it by 4.18 joules per grams degree Celsius, and then times it by 20 degrees Celsius. When you do all those calculations, you're going to get 167,200 joules. So it would take 167,200 joules of energy to heat that water.